Welcome students. Welcome to the video on the third module of electronic devices. So we are discussing about the bipolar junction transistors. So in the previous classes, we have discussed what is meant by bipolar junction transistor, how the current transfer will be taking, and what is the amplification factors. And also we have discussed what is the fabrication process of a transistor. So in this module, in this video, we will be discussing about the equivalent model of the transistor, that is Ebers Moll model. So we know that any device which is used can be represented in an equivalent circuit. So the equivalent circuit will enable the analysis of the circuit in a short form. That is, you can analyze the circuits using the internal parameters. So any device can be replaced by its internal resistance and capacitance, and that will give the equivalent circuit. Considering a transistor, we know that a transistor is nothing but two diodes when it is connected back to back. So here, when they are connected to back, and the base will be common to both the diodes. In addition to that, we will be having two current sources, and these two current sources gives the coupling between the two junctions, and those both the current sources will be interdependent. So the current source which is connected across the first diode, that is the emitter to base junction diode, will be depending upon the current which is generated by the other junction, that is the collector to base. So coming to the equivalent circuit, we can represent any transistor by its equivalent circuit as discussed. So here I take this is an PNP transistor. So here I know that a diode P and N will be forward biased in the emitter junction. So we can see here you will this is the anode part of this, and this is the cathode part of it. So the P and N, the N region is the base region here. Similarly, at the other end, this is a collector to base junction which can be replaced by a diode, and here it will be normally reverse biased. So this will be connected to the positive terminal of the battery, and this end is nothing but the base which is common here. And coming to the current source, we know that so this alpha R is nothing but the current gain of the transistor, and this R stands for the reverse current. So the reverse current is nothing but the current which is coming here, and ICD is the current gain, and it is a reverse current gain here, and ICD is the current which is coming from the collected device. And similarly, here when we see here, alpha F is the forward current gain, and I is a current in the emitter junction. So this IE and IC are the conventional current here. So here it is a PNP transistor, and the holes are the majority carriers, and we know that the holes will be moving from the emitter to the collector region, and hence the arrow mark is inside the device. It is entering into the emitter region. So this diagram is about the uh, Ebers model of an NPN transistor. So we can see that both the models are same. Or the only thing is the directions are interchanged here. That is, the conventional current will be flowing out from the device. So IE points outside. So also we can see here also, like the forward current is depending upon the reverse current, as well as the reverse current will be depending upon the forward current. So the diodes are not in isolation, so they are interdependent, and it means that the total current flowing in one diode is influenced by the other. When the diode is in isolation, then they are characterized by the normal diode equation. So the normal diode equation is given by I is equal to I naught into e power V divided by Vt minus 1. So we take the two diode as a different with no contact, then the forward current which is flowing in an NPN transistor can be given as IF is equal to IES, where IES is nothing but the emitter current into e power of VBE, the voltage which is applied across the emitter to base terminal, by Vt minus 1. Similarly, the current which is in the collector to base junction can be given as IR is equal to ICS into e power VBC, where VBC is the voltage which is applied across this terminal or measured across this terminal by Vt minus 1. So this IF is nothing but the forward current, and IR we take it as a reverse current. IAS is a reverse saturation current of the base emitter junction, and ICS is a reverse saturation current of the collector to base junction. So Vt is the thermal voltage, and VBE is the potential difference between the emitter to base junction across the emitter to base junction, and VBC is the potential difference across the emitter to, I mean, base to the collector region. So when these two junctions are combined to form a transistor, the base region is shared. Now we will be having totally three different currents, and we can evaluate all the three different current using the relations, basic relationship. Now we assume that both the diodes, that is the emitter to base, which we have seen in the previous slide, and the collector to base junction, that is the diodes, both the junctions are brought together. So now the forward current can be represented in terms of the reverse current, that is IR, and similarly the reverse current, that is the output current IC, can be represented in terms of the forward current IE. So the IB is nothing but the current which is coming into the base terminal. So in the forward mode operation, it is in the forward mode operation, alpha F of the current, emitted current, reaches the collector. That is, a portion of the forward current will be reaching the collector, and this means that the diode current passing through the base emitter junction contributes to the current flowing through the base collector junction. That is, here, if you see here, this current is given as IF, and this is nothing but alpha into IF. So collector current is nothing but alpha F into IF, where IF is nothing but the current which is crossing this junction. Similarly, in the reverse biased junction, we can, sorry, in the output side, we can say that there will be a current called as IR, and then the current gain in the reverse mode is given as alpha R. So I can see that IE will be equal to alpha F alpha R into IR. So both are independent. So IC is equal to alpha F into IF. This is the forward current. So IE is nothing but IF, and so IB will be equal to 1 minus alpha F into IF. So this is in the forward mode operation. Similarly, in the reverse mode operation, also we can say that alpha R times the collector current will contribute to the it will contribute to the collector current alpha R. Alpha R will be in the range of zero point 0.1 to zero point 0.5, which is nothing but the common collector current gain. So reverse mode operation is nothing but, in the reverse mode, my VBE is equal to 0. IF current is equal to 0. IE is equal to minus alpha F into IR. Similarly, IC is equal to IR. So total current IE is equal to IB plus IC, which I can say that as IR into 1 minus alpha R. So finally, we can say that any transistor can be represented in two modes. One is called as the normal mode, and another one is called as the reverse mode. So the normal mode equations are nothing but VBE will not be equal to 0, VBC will not be equal to 0, then we will be having the output current IC, which is equal to alpha F into IF minus R. And similarly, IE is nothing but IF minus alpha R into IR. So these two equations indicate that the IC is depending upon the forward current and IE is depending upon the reverse current. And similarly, the base current can be given in terms of the third terminal current can be given as, we know that IB will be equal to IE minus IC. So I can write it as 1 minus alpha F into IF minus 1 minus alpha R into IR. So these are the Ebers-Moll model equation for the terminal currents. So here we have discussed what is meant by Ebers-Moll model, how you can represent a diode in terms of how we can represent a transistor in the form of two diodes connected back to back, and how to derive the relationship between the three currents in terms of the forward mode gain as well as the reverse mode gain. And also in the forthcoming videos, we will be seeing the secondary effects of the transistors. So thank you.